This is AP Calculus 112. We're going to learn about confirming continuity on an interval. And your intervals, remember, can be in set notation. I just want to review that with you. If you have an interval like this, bracket, -1 to 5, and then parenthesis, the bracket means that the -1 isn't included, and the parenthesis tells you that the 5 is not included in the interval. So anytime you have brackets, the number at that bracket is included in the interval they're talking about. If you have a parenthesis, the number that they're talking about is not included. If you have something like -infinity to infinity, infinities will always have parentheses, never brackets, because you can't include all of infinity. There's no way to know what that is or how big it is. They will always be in parentheses. So bracket included, parenthesis not included. Okay? And for these problems, the directions are going to say, can the graph be continuous on the given intervals? And then they'll give you either a graph and intervals, or they'll give you a piecewise function and the intervals, and then ask you to graph it, and you'll have to look at what you ended up with. In this example, we've been given a piecewise function already graphed, and then they're asking you if the graph is continuous on the given intervals. And the first interval they want us to look at is from -5 to -2, and since these are brackets, the -5 and -2 are included. So if I look at -5, that is a closed circle there. And then if I go all the way until x equals -2, which is right here, I can look at that and see that there are no breaks, jumps, or asymptotes in that graph from x equals -5 to -2. You need to understand that the intervals that they're talking about, they're always talking about the x values. They will never be talking about the y values when you're talking about these intervals. So as x goes from -5 to -2, and as x includes -5 to -2, is the function continuous? And you can look at that function and see that you could draw it without lifting your pencil. So yes, the answer is continuous. So for that, we would say yes, it's continuous. Now let's look from -3 to 3. From -3 until you get to 3. Well, notice between -3 and 3, we have a jump in the graph there. So it's not continuous because we would not be able to draw that function without lifting our pencil. So that one is no. And then from 6 to infinity, if I look here at 6 to infinity, well, 6, we got to pay attention. Is this a bracket or is it a parenthesis? Here it's a parenthesis. So they're not including the number 6. They're including everything just to the right of 6 and all the way to infinity. So since 6 is not included, and it's an open circle here, it is continuous from that point on because the 6 isn't included. Now, if this had been a bracket, we would have to say no. But since it's a parenthesis and 6 isn't included, then it would be a yes. So there are some little specifics that you have to look for as you're dealing with the set notation, but it's pretty simple to deal with as long as you know that the bracket is included, parenthesis is not included. In this example, they're giving us a piecewise function, and they're just asking us if the piecewise function is continuous. So as long as you graph the function and see that there are no points where there is a jump or an asymptote, it will be continuous. But if there are any jumps or any gaps in the graph, you know it's not continuous. So here they don't really give us specific intervals to check. They're asking about the entire function. So what I would do to graph this, if I look at x minus 3, so slope is 1, y-intercept for that function is -3. So at -3, I have a slope of 1. So the line they're talking about there is this one right here. Now, they're only talking about the portion of this line that where x is less than or equal to -1. So at -1, I'm talking about this point right here, and that's the starting point for that portion of my function. So the rest of it, this right here, we're not going to include. We're only going to include from -1 left for that portion. Another way you could do that, you could plug -1 in. So -1 minus 3 is -4, so you know the point -1, -4 is on that graph. And then you know the slope is 1, yeah, so you would then draw it in that direction. So you could start at the end point if you wanted to and go from there, or you could draw the whole thing and erase the portion you don't need. Either way works. For the next one, when they give me an interval like this, where it's going from a number to another number, I tend to just plug those numbers in and then see what the endpoints are, and then consider what the graph should look like going from there. So if I plug -1 into this function, -1 squared is 1 plus 1 is 2. So I have the point -1, 2. And then if I plug 2 in, 2 squared is 4 plus 1 is 5. So I have the point 2, 5. And now be careful with one like this. That is a quadratic. That's a parabola. So you know it's not just a straight line. So you have to be careful. Don't just draw a straight line there. We have to draw the curve. If I think about 0, if I plug 0 in, 0, 1 is on the curve. If I plug 1 in, I get 2. And that gives me all the points I need. Now, one thing you need to understand is which points are included and which points are not included. So we need to look at the symbols here. This one just says less than. So if it doesn't have an equal to, then it does not include that ordered pair. So instead of having a solid dot here, I do need that to be an open circle. Okay? And then here, since it's less than or equal, that would be a solid dot. And then at 2x minus 3, that again is a piecewise function. -3 is our y-intercept. I could go up to right 1 to draw my line, that function right there. And that is as x is greater than 2. So that one doesn't start until 2, so I get rid of the rest of it. And it's just greater than, so it does not include 2. It's an open circle at 2. So this completes my piecewise function. Another way I could do that is I could just plug 2 in. 2 times 2 is 4, 4 minus 3 is 1. So at 2, I have the ordered pair 1. And then I would make sure I have an open dot there. And then from that point, I would count up to right 1 and continue that pattern. So if you look at this, all I have to do now, they're asking us if the function is continuous. Well, if you look at this, there are some jumps in the graph. You could not draw this graph without lifting your pencil, so it's not continuous. So the answer for this one is no. This problem has the same directions. Is the function continuous? So again, it's a piecewise. We're going to graph that piecewise function. If I plug -1 in here, at the x value -1, my y value is 1. And then from there, I know my slope is -3, so I could go from that point down 3, right 1, or I could go up 3, left 1. Look at that line. That is the case when x is less than or equal to -1. So anything to the left of -1 we will keep, anything to the right we will get rid of. And that is solid because it's less than or equal. So there's the first portion. For the next one, that's also linear. So if I plug -1 in, -1 plus 2 is 1. So at -1, 1. Okay, so that point starts off our new segment, and that's at the same point the last one was. So it looks like so far it's going to be continuous. If I plug 3 in, 3 plus 2 is 5. So at the x value 3, I go up to 5. Now, since this function is linear, it's just in y equals mx plus b form, I know that I just draw a straight line from each of those endpoints. So there's the second portion. So far, it's continuous. And then for the last one, if I plug 3 in, -2 times 3 is -6, plus 11 is 5. So at 3, I'm at 5. Okay, so that's the same point again, same ordered pair. And then from there, I'm going to do a slope of -2. So I go down to right 1. I could continue that pattern. And this one is going toward the right because x is greater than or equal to 3. Since it's equal, that point is solid. So it looks like that is my function. Is that continuous? Since there are no breaks in the graph, the answer is yes, it is continuous. This example is a little bit different. It says to find the values of a and b that make the piecewise function continuous. So remember, if the piecewise function is continuous, there will not be any jumps or breaks in the graph. So that means the endpoints that connect each of these 3 segments have to be at the same points in order for the function to be continuous. There are a couple ways to do this. We could solve it using a graph, or we could solve it analytically or algebraically. Okay, so you have options here. I tend to try to graph them and look at what I've got and then check my answers algebraically. So if you look at this, both a and b are in the middle function. So I'm going to avoid that function at first, and I'm going to draw the left portion and the right portion of that graph first. So if I do that, this function is x plus 1. That's a linear function with a slope of 1 and a y-intercept of 1. So if I just draw that part, I go up to 1, my slope is 1. So that graph is this linear equation, or this line. Now, I do know that it goes forever in both directions, but the only part of this line that I'm talking about is when x is less than 1. So what I'm going to do is I'm going to look at the x value of 1. I know I'm only including the values that are to the left of 1 because x has to be less than 1. And here it says that x is just less than 1, so it's not including 1. So right here at the 1, I'm going to draw that as an open circle. Next, I'm going to do this equation. And that one is 3x, y equals 3x. Well, there, the y-intercept is 0. And if I go up 3, right 1, I have this line. Now, in this one, this one doesn't start until the x value is 2. So rather than having to erase through that line, I'm just going to start this one at x equals 2 and go from there. So that one goes up in that direction, and this is greater than or equal to 2, so this one would be a solid dot. Okay, so I don't need those ordered pairs anymore. So in order for this function to be continuous, this function right here in the middle, I would have to have values for a and b that cause this point and this point to be the endpoints I get when I plug in 1 and 2. Okay? So when I plug in 1 and 2, if you look at this graphically, the ordered pair that I want to be right here in order for this thing to be continuous is the ordered pair 1, 2. Okay? So now, my function for that middle section is y equals ax plus b. And I want this ordered pair right here to be the ordered pair 1, 2. All right? For the second portion, I want that ordered pair to be 2, 6. So my second ordered pair, I want to equal 2, 6. And it's for the same equation, y equals ax plus b. So since I have an ordered pair for this function and an ordered pair for this function, I can plug in the x and the y value in here. So if I do that, 1 goes in for x, so a times 1 is just a, and 2 goes in for y, so y is 2. Over here, I can do the same thing. Y is 6, a times x is 2, so that's 2a plus b. Now, if you look at what you've got, you have a system of equations. You've got 2 unknowns. So what I'll do is I'll line these up. I'm going to get, well, my b's, notice, are the same. So if I just put this one underneath this one, 2 equals a plus b. Then to eliminate the b, all I have to do is subtract these two equations from each other. So 6 minus 2 is 4. 2a minus a is a. B minus b cancels. That means a has to be equal to 4. Then if I plug 4 back in up here, 2 equals 4 plus b. If I subtract the 4 over, negative 2 equals b. So a is 4, b is negative 2. We have solved the equation. And you could double check that. If we look at that equation, it would be y equals 4x minus 2. Okay, so if that's the equation, at 1, if we plug 1 in, 4 times 1 is 4. 4 minus 2 is 2. That's the ordered pair 1, 2. So that does shade in that dot. And then at the x value of 2, which would be this point here, 2 times 4 is 8. 8 minus 2 is 6. 2, 6 is the other ordered pair, and that forces those to be continuous. I've shown you the graphical approach for this one. I want to show you the algebraic approach. Some people prefer to not graph anything and just do it by hand, and that's fine. Basically what you would do here, notice in a piecewise function, you will have all of the domain represented here. So this goes from negative infinity all the way up to infinity, because x is less than 1, that's going from 1 in the left direction. This is the portion from 1 to 2, and this is the portion from 2 to infinity. So you have every x value included here. Notice the end value here is going to be the start value for this middle function, and the end value here is going to be the start value for the last function. So as long as we can plug numbers in and get ordered pairs, we will be able to solve this algebraically. So now, looking at this function here, if I plug 1 in, I get 1, 2. So if I plug 1 in for x, I need the ordered pair 1, 2. And then looking at the bottom, if I plug 2 in, I get the ordered pair 2, 6. So this is the end point for the first function, and this is the starting point for the last function. I need this end point and this starting point to be the same ordered pairs I end up with in the middle function. Okay, so if I plug 1 into the middle function, 1 times a is a plus b equals y, which was 2 in that case. And for this one, if I plug 2 in for x, 2a plus b equals the y value 6. So now I have the two equations with the two unknowns. I can use my Algebra 2 skills to solve this system of equations. I'm going to just put this one over here. And at this point, it's the same as the problem we've already done. I'm going to subtract. So a is 4. If I plug 4 back in, b is negative 2. Okay, so some people prefer the algebraic method rather than graphing. To me, I like pictures, so I tend to graph them. It's up to you how you solve the problem.